Hi everyone. Thank you for coming to our talk. Yeah, as Matthew said, today we'll be talking about how to use Ray Data and Anyscale to optimize your batch inference workloads. So I'm Scott, software engineer at Anyscale. I'm working on Ray Data, and I'm joined by Richard, who's a product manager. Cool. So quick overview of today's talk. First, I'll go over the basics of batch inference, and then I'll talk about why you should use Ray and Anyscale for batch inference. Then we'll compare it to other solutions out there. And finally, we'll introduce Ray LLM Batch, which is a framework for cost-efficient batch LLM inference. So what is batch inference? Batch inference workloads typically are workloads which generate model outputs from a large input data set. And these are often referred to as offline workloads. And some defining characteristics are that they have a very large data scale, so often hundreds of gigabytes, terabytes, or even larger. And they have a big focus on high throughput and low cost. And this means that they often have a loose latency requirement. And it typically involves deep learning or other models that have heavy GPU computations. And below, this is what a typical batch inference workload would look like. You would start off by reading in some files, maybe doing some pre-processing on the data before passing it to your GPU model. After that, you might do some post-processing and then write out the results to some cloud storage. And batch inference workloads typically permeate many business use cases, right? They're very, very common. Some example workloads might be for like text and image embedding generation, image model batch inference, and LLM batch inference. And some common alternative solutions out there for running these workloads include OpenAI, SageMaker, Spark, and Bedrock. Now, so far we've discussed a lot about offline batch inference, and now I'll take a second to compare it to online inference. So online or real-time serving workloads are a little different in that they want to minimize latency. And these workloads are very different, and so they require different configuration of like code, optimization, and compute. And specifically for LLM workloads, this means that we're going to have to use different optimization techniques and compute to really optimize our objective. So for offline workloads, we want to maximize throughput and minimize the cost. And so we'll use optimization techniques like pipeline parallelism and KV caching. For these types of workloads, we can often use cost-efficient GPUs that are more widely available, like A10Gs and L4s. For online real-time inference workloads, we want to maximize reliability and minimize the latency. And so we'll use techniques like speculative decoding and tensor parallelism in order to achieve them. And these typically require the use of higher-end GPUs like H100s and A100s to really minimize the latency. Now, let's compare what these workloads look like at a high level. So taking a glance, the online real-time workloads look pretty similar to the offline batch inference workload that we discussed. They need to take the user query, do some pre-processing, pass it through the model, and then maybe do some post-processing before returning the response. But because of these different techniques and optimizations that we discussed, they actually they run into different problems that we'll need to figure out. And so for offline batch inference, we run into problems around like GPU utilization, fault tolerance, auto-scaling for these really large workloads that involve like terabytes of data running for days or weeks. Whereas for online real-time inference, we'll have to tackle problems around request routing, load balancing, and LLM multiplexing. Cool. Next, I'll turn it over to Richard, who will introduce Ray and Anyscale stack for batch inference.
Hi, everyone. Thanks, Scott. So what I'm going to talk about now is some of the sort of core problems from a technical perspective on how we think about batch LLM inference, or batch inference and then batch LLM inference. And we'll also then talk about how the Ray/Anyscale solution sort of addresses these problems from a technical perspective. So again, as Scott mentioned, there's sort of two standard ways of doing batch inference, especially with deep learning models nowadays. One is to reuse an existing data system, such as Spark or Flink, or to repurpose an online deployment, something running on something like Kubernetes. And both of these sort of techniques actually come with some major limitations, which I'll expand upon next. For existing data systems, from a technical perspective, there's a couple of limitations when it comes to doing batch inference with deep learning. First of all, you need really great GPU support, especially when you're working with deep learning models. And you need to utilize these GPUs well. And therefore, you don't really want to have a bunch of GPUs sitting idle waiting while the CPUs run, or as sort of pre-processing or post-processing steps run. So the second part is that you need support for great parallelism, especially in a sort of expressive way. These models are often very large, and therefore it's actually quite necessary to have some sort of hierarchical parallelism. For example, being able to do data parallelism, which is very standard in these data processing systems, and within that having some support for tensor parallelism or pipeline parallelism. And finally, similar to other systems, it needs to be reliable, it needs to work at scale, it needs to have all the standard data connector supports. Compared to online serving systems, which is the other sort of alternative for deploying batch inference solutions, you will often see these sort of three limitations. The first is having some overhead from other components, such as load balancing components or proxies. And these typical things are typically, again, built and constructed in a way that are architected for good latencies, but not like massive gigabyte throughput. The other thing is you have to manage the online service separately from the actual batch system, which leads to sort of a two-tiered deployment model and having sort of observability that doesn't work across the stacks. And finally, for larger models, again, as Scott mentioned, you'll configure things differently, right? You might target sort of SLAs for online deployments, in which case you will sacrifice some throughput. Overall, what we often see is that, like, especially for NVIDIA GPUs, you can max out throughput much more effectively than you can and achieve a much greater sort of token throughput or image or input throughput per second compared to when you optimize things for latency. So talking a little bit about the sort of the Anyscale sort of philosophy and approach to the solution is we sort of look at this as a full stack problem, right? We start off with a Ray Data, which we've had numerous talks on over the course of the summit. Ray Data is a distributed data system for unstructured data processing. This is built on top of Ray Core, which is a distributed runtime for scaling AI and data workloads. And underneath, so Ray Data and Ray Core can run on any cloud, but in particular, Anyscale provides capabilities for scaling across clouds. So talking a little bit more about each layer, just as a primer, Ray Data comes with sort of scalable and fault-tolerant APIs for data processing, especially for unstructured data. It integrates very closely and is built as a Python-first sort of system. So pandas, NumPy, PyArrow, these things are core components of Ray Data and interoperate nicely as compared to other systems that might be built from the Java world. This allows for interoperability between the machine learning ecosystem and also the data ecosystem. And finally, there's sort of streaming execution, which allow for really efficient mixed CPU and GPU execution. And I'll talk a little bit more about this next. As an example, it's typically really important to have CPUs and GPUs fully utilized together at the same time. However, this is sort of a core limitation in existing systems like Spark, where scheduling is fused as all the stages within scheduling are fused together, regardless of the resource requirements. This means that in a typical single cluster setup, the total parallelism is limited by your rate limiting factor, which is probably the number of GPUs that you have, leading to underutilization in CPUs. We've also tried doing things like stage scheduling, but that unfortunately has run into limitations when using GPUs. But this fundamental limitation means that GPUs are idle when there is sort of underutilization of the resources, and also GPUs are completely idle when there is other sort of processing steps that are happening. On the other hand, Ray Data is able to sort of stream the data more effectively and execute the CPU and GPU steps simultaneously if written in a sort of streaming fashion and with a streaming executor, leading to a much more efficient sort of batch inference step. So we do have a blog post that talks a little bit more about this, and we'll have a QR link later in the talk. Ray Data is built on top of Ray Core. So Ray Core provides this scalable foundation. First of all, with primitives to express very flexible GPU scheduling, specifically for sort of fine-grained compute tasks that may be asynchronous and leverage the GPU. This is sort of unique in the sense of there's not many other distributed systems that are able to sort of offer this functionality. Another thing is stateful actors, which allow the system and sort of programs to hold expensive models in memory, allowing for sort of the caching of these objects and not needing to sort of rematerialize and re-download these things, which can be very expensive. And finally, as mentioned before, the Ray core does come with nested parallelism, which makes it really easy to express data parallelism, model parallelism, and sort of construct a batch system that's uniquely suited for models that are getting bigger and bigger. And finally, just to quickly sort of talk about Anyscale infrastructure. Anyscale infrastructure comes with a variety of different sort of functionalities that are really relevant for this type of workload. Cross-zone instance searching to find GPUs at the lowest rates, being able to support small instance fallback onto on-demand to best leverage small instances for cost savings. Also comes with accelerated model loading, as we have multiple demos of, to sort of demonstrate and have the capability of quick startup of large model replicas and also extensive observability across the stack. So now I'll hand it over back to Scott to talk a little bit about the code examples and results that we have for standard batch inference.
Thanks, Richard. Yeah, so let's take a look at how we might implement one of these batch inference workloads with Ray Data. So this is kind of the layout that we've seen before. And just to give a quick example of how you might implement this, you'll start off with one of the many read methods that Ray Data provides. So we're very flexible in the data input and output formats. We support very common formats like JSON, CSV, images, videos, and as well as like SQL-based databases and much more. You can check out more on our docs. So yeah, you would do that read, and then the next step would be doing this pre-processing step, which we can express with like a map operation. And so in this case, we're just applying kind of the stateless transformation to each row of the data set. So we can use this task-based or stateless map in order to express that. The next step is going to be applying the GPU model, the GPU-based model. And so for this step, what we want to do is actually use this actor-based or stateful map function to do it. And so this means that you just need to load the expensive model once on your GPU, and then you can continuously, repeatedly call with whatever batches that you're passing to it. And Ray Data makes it really easy for you to configure like the concurrency as well as number of GPUs that you're using on per worker. So you can test with very small amounts of data locally or just on a small cluster, and then you can scale up very flexibly and easily to whatever production workloads you have in mind. Finally, you might do the same kind of like post-processing per each row, which you can do with a map function. And then finally, you can use any of our write methods to write out the results to whatever cloud storage, local disk, etc. Cool. Now let's take a look at a few case studies on how we actually apply these workloads. So this is an example of taking some input PDFs and generating a bunch of text embeddings. And so for this example, we took about 2,000 PDFs, which has like 30,000 pages. And we were able to generate about 140,000 encodings. So for this workload, we used 20 GPUs, and it took about 4 minutes to run. And the estimated cost, if we use AWS spot instances, is around 95 cents. Right? So you can see from this graph here that we have basically 100% GPU utilization, taking advantage of that streaming execution to really maximize how much GPU utilization we can get. This is another example of using generating text embeddings. So we use the Falcon Refined Web dataset for this, which is a 1.68 terabyte dataset. And using 320 GPUs for this large workload, this took about 18 hours to run in total. And the estimated cost on Anyscale was around $6,000 to run this workload. Finally, here's an example of batch image inference. So just comparing Ray to kind of these other solutions, Ray is up to 2 times faster than Spark on this particular workload, and up to 17 times faster than SageMaker. Next, I'll turn it back over to Richard, who will talk more in depth about LLM inference.
Thanks, Scott. So this is one of the more exciting sort of Ray Turbo announcements, which is some of the work that we've been doing for batch LLM inference, in particular on Ray/Anyscale. So just as a refresher, batch LLM inference is basically very similar to a lot of the graphs that that Scott has been showing, except the LLM inference stage has models that are themselves possibly distributed much larger. So we're excited to announce Ray Batch, which is a proprietary library built for large-scale, cost-efficient batch LLM inference. It's built on top of an Anyscale inference engine and Ray Turbo data with Ray Core and Anyscale. This allows you to bring any sort of open source model that's available on VLM because our Anyscale inference engine is built off of VLM. It's fault tolerant, allowing you to leverage small instances at scale and achieve massive cost reductions. And then it sort of also comes with a optimizer for custom workloads to configure and optimize your engine settings properly. Let's dive into a quick example of what this new library looks like. So it's actually quite simple. It allows you to express a workload, and we'll cover what a workload means. And we will be able to pass that into the batch, batch LLM pipeline, and you can just execute the pipeline with run. And what this returns is a Ray data set, which then you can do more post-op operations as well. Now, let's dive into what this workload API actually looks like. So it's quite simple. Effectively, you should be able to express where your data set is located and have sort of the ability to do some pre-processing of the data set within this API, within the load data set sort of abstraction. There are some specific parse row sort of operators so that you can express like how exactly you want to massage the data, so that maybe for example you want to map it into like an OpenAI chat sort of API, so that you can do batch inference in that setting. It also expresses the ability to provide sampling parameters, which also in here you can plug in sort of various things like temperature, max token, so on and so forth. The abstraction also allows you to do some sampling from a dataset perspective, so that you can operate on a fraction of the dataset at once. So again, this workload is plugged back into this Ray batch, which takes in two things: the workload API and also a configuration file. Now, the configuration file is quite straightforward. You can express which model you want to run, and then also some number of engine keyword args. And accelerator type. Now, a couple of nice things here is that we also have an optimizer, which will sort of automatically tune some of these or most of these engine configurations for you given the workload. And also right now we have to specify a particular accelerator type, but we're planning to expand this to feel a little bit more serverless, allowing you to express a class of accelerator types, and we'll be able to sort of mix and match overlap. What's really interesting about this is that given the accelerator type, the configurations will be different. So we will also, the optimizer should be able to take advantage of that. So again, putting it all together, this is what like a typical Ray batch abstraction will look like, and it should be quite easy to sort of express these batch inference workloads very easily. And when you run pipeline.run, this is like it will run like a typical sort of execution of like the read, tokenization, inference, and so on and so forth. So in comparison to alternative solutions, the Ray batch with its optimized configurations is able to achieve up to 2x sort of lower price than Bedrock, and this is Bedrock with batch pricing, right? So it's Bedrock with 50% off. Is in the FP8 model, we're able to achieve up to 3x, and this is again for a Llama 3 8B model. And then with prefix caching, which when you have sort of shared prefixes, we're able to achieve up to 6x AWS Bedrock with batch pricing. So on larger models, for FP8, we're able to achieve 20% off Bedrock batch pricing, and for prefix cached workloads, we can achieve up to 2x cheaper than batch pricing on AWS Bedrock. And I think the other thing that's not noted on the slides here is that these were all achieved using L4s and L40s. So not needing A100s or H100s, pre-reserved instances, and so on and so forth. Yeah, so the other thing that I would note is that we compare for FP8, it's actually not really clear what Bedrock itself is using. They may be using FP16 and FP8, so that's why we kind of try to demonstrate both numbers. And the last thing is that there are limitations on the Bedrock side in the sense that if you use batch pricing, it will sort of take up to 24 hours to return, especially for OpenAI as well. And whereas for Anyscale Ray LM batch, the solution is able to start executing as soon as you acquire instances. And typically for L4s and L40s, those are quite instant to acquire. So the roadmap here moving forward is to start focusing on optimizing these and expanding our optimizer to sort of leverage these multimodal models. Pixtral 3.2, Molmo is also sort of on our radar. We'll pick a couple and sort of focus on large and small as well. And we believe that there's huge rooms for cost optimizations there. On the proprietary side, we will sort of be releasing our or engine optimizer API for public preview so that there's anyone on the Anyscale platform is able to leverage it. And we obviously have sort of engineers continuing to burn down kernel optimizations to improve throughput. So to recap, we sort of talked about, as a very high level, what batch inference is about, why Ray and Anyscale are a great fit, what's the sort of results, and we also introduced Ray LM batch, which is a cost-effective batch LM inference library. So I think that's basically it for this talk, and thank you all for attending, and happy to take any questions at this point. Is there a mic?
No, we don't have a mic.
Okay.
Did you investigate the reasons why SageMaker was 17 times slower? Any thoughts on why? For the image resonant example.
I don't recall the exact reasons why SageMaker in particular was slow. I think it's just a combination of like all of the Ray Data and Anyscale optimizations that kind of combined all together as a stack.
Yeah, I think the API itself was a little like the SageMaker API is a little bit transparent, or like, you know, it's not very, or opaque is the right word. It's like not very clear where exactly is the way to optimize it. And there's also four or five different offerings for batch transformations on SageMaker. So we chose the one that was marketed more clearly towards this particular use case. It may be like the results may be different at this point, but we would be happy to update these numbers if that was the case.
So in the example that you showed, Marin, you had some code snippets on the pipeline doing pre-processing in the model. Do you guys support prefetching onto the GPUs further ahead? Yes. Do you guys support prefetching onto the GPUs?
Yeah, so the question was, do we support prefetching onto the GPUs when we like kind of run these GPU-heavy map batches operations? And I think for map batches, we currently do support like prefetching of batches, and you can configure that when you use Ray Data. Yeah.
Derek? Yeah.
Can results be materialized like periodically during a long-running batch job?
Can results be materialized? Yeah, so do you want to take this one?
Yeah, so I guess by materialize, if you're referring to just like writing out the results somewhere and not like in memory, this kind of works as like our Ray Data has streaming execution, which means that like whenever it's done processing some amount of data, it's able to kind of send it to the next task. So the entire like Ray Data job doesn't need to run in order to write all the data. It'll kind of write things as they're being finished. Yeah.
Which embedding model did you use?
For the
I believe it was
the
GTE large.
Yeah, which is an open source model by Alibaba.
And like, how long will it take? Like, say somebody starts this process, and how long would it take before results start to appear?
Like basically the first results to come out, right? It should be like maybe like seconds or minutes, basically. Yeah.
Do you get any observability on being able to see the intermediate object store values for intermediate results that are being consumed by subsequent steps?
So the question is, do you get to see intermediate representations of the objects that are being stored and saved? And right now, by default, I don't think we have that sort of.
Yeah, you could kind of get into the weeds of things by like using some debugging, like debugger, like a Ray debugger that we have to like inspect individual objects. But I would say for most use cases, it's not really typical for like there's no real use case for like looking at individual objects. Usually they're just like represented at kind of as these like object references, and that's what gets passed between all these operators.
I have a question. In your engineering realization, do you have any special optimizations for the GPU memory management in order to improve the data loading or write efficiency, something like this?
So this is for regular or LLMs?
Yes,
Regular and LLMs?
yes.
Oh, for LLMs, we have spent a lot of time sort of optimizing sort of the KV cache patterns, and right now we're exploring some ways to sort of have better sort of coordination between the prefill and decoding steps, so that there is a little bit better sort of utilization and throughput, trading off the latency.
Another question is, in your daily work, do you have any best practice of how to do the profiling for the online serving system? Because you know it's a synchronous system, right? Do you have some best practice also?
For online serving systems?
Yeah, serving, it's a synchronous. How could you monitor the system performance and then the bottleneck?
So I'm happy to refer you to the folks that work on the online serving systems, but this is more of a batch system talk. Yeah.
The LLM batch library, is that be open source or is that only proprietary?
So currently the plan is to keep it as proprietary, but we will have sort of like examples in the open source, especially in the VLM repository for how to do some basic versions of batch inference. Obviously, like the tuning and stuff like that will be much more optimized on Anyscale. Yeah, Derek.
I think you mentioned previously that checkpoint and restart would be available eventually. Is it available in this preview release?
Yeah, so checkpointing. So actually, Scott,
Yeah, actually,
sorry.
I'm working on this right now. We're basically like in the preview stage, and we're trying to run it on like larger workloads, and then soon we'll make it available to like all customers. Yeah.
Actually, a follow-up on this. So, is that checkpointing and fault tolerance for the entire Ray data that's going to be launched soon?
That's right. Yeah. It's for like Ray data in general. Yeah.
I thought that's a proprietary feature.
Yeah, for Ray data, it works on Ray data on Anyscale.
Yeah. So like Ray Turbo data. Yeah.
Yeah.
So you're not like making it open source, right?
No, yeah.
Yeah.
For the data you write back, are you able to specify the size without the same like 128 something? Then actually write for remote HDFS format files, you don't actually the very large file on your
Got it. So the question I think was with Ray data, when you're writing files, can you specify like the output file size, right?
The first question is specifically the size. The
Uh-huh.
I see the writing for a smaller size, 2 megabytes or something. Also, second question, I mean, if you can write to like HDFS or some S3 server, we don't actually keep it a large file storage on the WeHat, and then possibly run out.
Got it. Yeah. So for the first question, the write APIs don't have a direct like file size target, but we have a way to specify like the number of rows in the output file. So that's like a kind of a proxy of doing that. And then for the second question, because Ray data uses streaming execution, it will essentially like not keep too many files or too much like data that is to be written out like in memory. As soon as the results are available to be written out, it'll basically do the writing out. So you won't run into problems where you have like a bunch of intermediate blocks that are like waiting to be written, and they're just like holding up memory. Yeah.
Any other questions?
Yeah.
So you had a slide on the future roadmap for multimodal. Do you you have a rough timeline when it will be available and what are the challenges?
So it'll be Q4. This will be a hot topic in Q4, and given the sort of proliferation of new models, we plan on sort of having announcements by the end of the year.
But do you have a decision of what problems that you see over there?
So one of the big differences for multimodal models is that the data size becomes a little bit larger, and you have to embed the data into the text. So we'll be sort of tackling that challenge. The second one is that there are sort of optimizations that we can do in order to take advantage of these architectures that are a little bit more split, not so homogeneous. And so we will be taking advantage of that for that as well.
Which models do you support?
So right now, we support. I think you'll get the best performance for large LLM models that are available on VLM. We will probably be doing some extra tuning for multimodal models, because we believe there's opportunity there, and also for very, very large models like 405B. Those things I think you will see a little bit less performance optimization, but that's currently, but that we believe that's some room for us to improve on. Cool. I think we'll finish up here, and then we will take more questions on the side. Thank you, everyone.